All right, as I was saying in the last video, in 1989, Voyager 2 went past Neptune, gave us, our best pictures of Neptune, as well as its large moon Triton. All right, so and by the way, we're still in touch until the mid probably 2026 or so. We are still in communication with both Voyager 1 and Voyager 2, which have now technically left the solar system and are out in interstellar space. Now they're still about 4 light years from the nearest star, and they're not even heading in that direction. Their fuel supply, the reason that we're still in contact with them, the fuel supply that generates electricity is actually from nuclear power. So there's some radioactive material on these spacecraft, which were launched in the 1970s. So it's pretty amazing that we're still, that 1970s technology. We still can gain information from them. All right, so let's move on. And of course, there's been different spacecraft since the Voyager missions. The Cassini mission arrived at Saturn in 2004 and orbited Saturn for many years. It took lots and lots of photographs. It gave us incredible insight into Saturn and its moons. In particular, there's one moon called Enceladus. We'll talk a lot more about that. Which this moon has liquid water inside of it. And we even saw saltwater geysers coming from this little tiny moon Enceladus. So it's very interesting area of study. And by the way, the Cassini spacecraft it was eventually it was just a few years ago plunged into Saturn itself, into the clouds. Remember, these gas giants are just that. There's no solid surface, and so it's just thicker and thicker clouds. Jupiter is large enough we think that it probably has at the very center of it a metallic hydrogen, that the hydrogen is condensed, crushed so much by gravity that it's actually formed metal, metallic hydrogen. And that may or may not be the situation inside of the center of Saturn. Remember, Saturn's not nearly as big or as massive as Jupiter. Of course, Jupiter's had its own spacecraft going. Probably the most famous one was the Galileo spacecraft. The Galileo mission lasted for more than a decade. Gave us lots of information about Jupiter and its moons. All right, so keep going. The question is, how did the solar system form? And one of the models that we use is this nebular contraction. That is, this cloud, which by the way, we see these clouds of gas and dust in all parts of the galaxy. Right? They're still out there. There's still solar systems forming today. And of course, we think that our solar system formed about 4.5 billion years ago, from a similar cloud of gas and dust, and that gas and dust probably got rotating. Different parts of it were probably rotating in different directions, but maybe this is speculation. There's actually computer models that try to emulate this. So let's say some nearby star passed by and got the entire cloud rotating more or less in the same direction. And of course, for us, that would have to be counterclockwise, as looked down from the north. If you think about the celestial pole, the celestial North Pole, and if you were to look down on the solar system from that, that would be rotating in a counterclockwise direction. Now, this cloud started off not as a flat disk; it's certainly a three-dimensional object that has volume. The physics of this thing collapsing down into a disk is actually very, very well understood. It's called the conservation of angular momentum. It's the same reason, for example, that when you look at a skater and she's spinning around on her axis, and she pulls her arms in closer to the center of her body, she starts spinning faster. Not because she's given more torque or anything like that. It's just because of the conservation of angular momentum, and that's the same thing that happens in these giant interstellar clouds. We actually see this, in other solar systems forming, and of course, eventually, you have from those clouds planets form, and there's actually various ways that we think the planets formed. One is called accretion. Here, let's move on to these next slides. Actually show that. So here's the conservation of angular momentum as the cloud as gravity pulls the cloud in towards itself. It gets smaller, and of course begins to rotate and flatten out into what is now known as the plane of the solar system. Right? That is why all the planets more or less line up in a nice flat plane. All right. So as I said before, this is observed. Here's an example of such a cloud within our galaxy. What can happen is what's called condensation, right? If you think about what condensation is, that's the our atmosphere, for example. That's a good model that we're using. Condensation happens when water molecules in the atmosphere, which are gaseous, combine to form a liquid, and then that has to do with temperature and density. And similarly, that happens with these gas clouds. At first, they start out very, very large. In some cases, many, many light years across. And as I said before, if let's say some passing star goes by and gets the whole thing rotating, more or less in the same direction, then you can have this contraction due to gravity, and then condensation takes place, and then what happens is accretion is when these things start to get large enough so that they're gravitationally attracted to each other, and so you start to build up from little tiny clumps to larger and larger clumps, so that gravity takes over, and then you have larger and larger planets forming, and then the things that don't form into planets become like the asteroids, what's called the solar system debris, if you will, things that didn't go into planet formation. And one of the things that we're not talking about at all quite yet is collisions. Inside of this thing, as planets and these what are sometimes called planetesimals, that is, they're smaller than what we would consider planets. When these planetesimals begin to collide, some of them will actually stick together. Some will collide and just obliterate each other. But when they start to stick together due to gravitation, that's what accretion is. And so sometimes they collide in such a way that you get a larger clump. All right. So we think that the terrestrial planets formed, closer to the sun than the outer gas worlds. Although that theory has actually been challenged lately, because there's the high enough temperatures. As it says, nothing else could condense them. Could condense closer to the sun, you're not going to have, like water vapors condensing into planets, right? That's only going to happen farther out from the sun, like far past the orbit of Mars, right, where the gas giants start, right? We're really past the orbit of the asteroid belt. All right, so there's you have the rocky worlds forming in the inner part of the solar system, and then the gas giants forming in the outer part of the solar system. At least that's one theory. As we're going to see, there's still some questions about that. The Jovian planets and planetary debris. So there are certain stars called T Tauri stars. These are, this was like the first star that was found that was like this. Is a star in the constellation Taurus called T. It just doesn't have a very good name, but anyhow, there's a whole class of these type of stars now called T Tauri stars. These are in their active phase of their evolution, and they have what are very strong solar winds that we can actually observe this material coming out from these stars. And the winds tend to sweep away the gas disk, and it just leaves rocky planetesimals and of course giant gas giant stars. So if there's any material in gaseous form in between the planets for these T Tauri stars, that gaseous material just gets blown out into the outer part of the solar system. That's what this is saying. And of course, that's perhaps what forms the Oort cloud, right? This cloud of material way out beyond the Kuiper belt, which is where most of the comets come from, we think. All right, so again, more about that stuff a little bit later. So the Jovian planets, the gas giants, they formed by accumulating this gaseous material far enough from the sun, so that that stuff is still kind of in the almost like a liquid form, gaseous liquid form. It's too close to the sun, planets forming too close to the sun, that would, the sunlight would just evaporate it. So basically these Jovian planets are capturing all the gas that's in the outer part of the solar system. Or another idea is that another idea, as I mentioned just a second ago, is that these things might not have formed from accretion at all, but directly from these little instabilities, gravitational instabilities in the outer part, in these cooler regions of the nebula, as the nebula contracted inward. All right, so those two models, if you will, we're not sure which one actually happened. We're still trying to figure this out. Lead to different things. Detailed information about the cores of the Jovian planets, which we're still trying to figure out, will help us distinguish between those two possibilities. Right? Remember, the two possibilities are, once these things are large enough, they capture the gas from the contracting nebula, or they might not have formed from accretion at all, but directly from these little instabilities in the outer cooler regions. So we're still trying to figure that out. And then there's still another possibility that some people have proposed, and that really has to do with our observations of other solar systems. It turns out that maybe the Jovian planets formed closer to the sun and migrated, formed further out and then migrated inward. Okay. So I'm about to run out of time. I'll continue with the next video.